In this video, we're going to talk about methods of optimization in higher dimensions. First of all, generalizing the second derivative test that we learned in Calc 1 to higher dimensions and learning a test for that. And then also we're going to talk about a new method called Lagrange multipliers that is probably unlike anything that you would have seen in Calc 1 or anything like that. But anyway, there are these two methods, and I really wanted to spend a little bit of time in this video primarily focused on emphasizing the differences between the cases in which you would use each one of these methods for optimizing whatever function it is that you're working with. So we're going to start by introducing the second derivative test and then Lagrange multipliers, and then look a little bit at how they're different. So second derivative test. Sounds super familiar. Because you learned a second derivative test in Calc 1, like I've already said. And just to kind of give an overview of this, the purpose of this is to classify what we call local extrema. Okay, so they may not be the largest values or the smallest values overall, but there might be just like a small dip or a valley or something like that that would cause it a little peak or whatever to show up. And the idea behind this is, first of all, that we have to suppose the second partial derivatives of f are continuous on a disk with center at AB. And we suppose that we're working with a critical point, or more generally, I guess, or more specifically, that the gradient of f of AB is equal to 0. If we let d at xy be defined to be the partial with respect to x twice at xy times the partial with respect to y, or the second partial with respect to y at xy, minus the mixed partial at xy squared. We now have a sort of a classification test that we can use that's really, really similar to what you would have seen in Calc 1. The first case is that if this whole expression here is greater than 0, then we have two cases that we want to look at. We want to check to see if the partial derivative with respect to x, or second partial derivative with respect to x, is less than 0. If that is the case, then we have a local max that we're looking at. So this is exactly the same as it was in Calc 1. Second derivative less than 0, you have a local max. If your second derivative with respect to x is greater than 0, then again, same as in Calc 1, we have a local minimum. And this is if this whole expression here evaluated at that point is greater than 0. Now, the second case is one that maybe you don't run across, you definitely don't run across it when you're working in 2 dimensions, and that you probably have not seen before, is this idea of a saddle point that can come up if this thing is less than 0. Well, okay, so a good question to ask really quick, though, is well, what exactly is a saddle point? A saddle point is really more or less exactly what it sounds like. It's a point at which the graph kind of forms the shape of a saddle. And what that really means, though, is that your derivative in your x direction, your derivatives in your y direction are kind of doing different things. So here's kind of a general sketch of what a saddle point might look like. It'll look like you have maybe like a parabola going in the y direction, and then maybe a parabola going in the x direction as well that faces downwards, though, instead of up. Instead of everything facing upward or everything facing downward, you have these shapes where they're kind of going in opposite directions. A real life example of a shape that looks kind of like this would be a Pringle. So if you have any Pringles handy, feel free to go look at those, maybe eat a few. But the idea here is a saddle point occurs when all of this is less than 0, and that just means that your graph looks like a Pringle instead of a bowl that's opening upwards or opening downwards. So I wanted to do an example that kind of walks through the whole process of using the second derivative test, and then we'll launch into Lagrange multipliers. So in this example, we are going to find local minima and maxima using the second derivative test for the function f of xy equal to 8xy plus 16 over x plus 32 over y. Okay, so before we can do anything else, before using the second derivative test, same idea as in Calc 1, we need to find critical points first. So we need the gradient of fxy to be equal to 0, or the gradient of fxy to not exist. Okay, so to find the gradients, we're going to take the derivative of this right here with respect to x first, and you're going to get 8y minus 16 over x squared for your partial with respect to x, and then the partial with respect to y is 8x minus 32 over y squared. Okay, so I'm going to set each of these equal to 0. And 8x minus 32 over y squared equals 0. Rearranging this right here, I'm going to get that, I'm going to move this over, divide both sides by 8, and I'm going to get y is equal to 2 over x squared. And then similar process over here, I'm going to wind up with x is equal to 4 over y squared. Okay, I'm going to go ahead and substitute this into here. Or actually I take it back, vice versa. I'm going to substitute this into here and solve for x. So x equals 4 over, it's going to be 2 divided by x squared, and then all that is squared. We can kind of simplify that down a little bit, and we get x equals x to the 4th. And the only way that this is possible is if x is equal to either 1 or 0. Okay, in the case that x is equal to 1, we look back up here with this expression with y, and we're going to see that y has to be equal to 2. So I don't worry about that situation with 0 here in a second, but 1, 2 winds up being a critical point. Now the situation with x equal to 0, we can't really plug 0 into this. That doesn't work very well. In fact, we can't really plug 0 in for x or y for this gradient here. So the gradient of f does not exist at 0, 0. So 0, 0 does wind up being a critical point. And then we also know that 1, 2 is a critical point. All right, so now we have our critical points and we're ready to do the second derivative test. And we're going to do this to 0, 0 and 1, 2. All right, so before we launch into this though, let's go back and check what our conditions were for that second derivative test. We had the requirement that our second partial derivatives are continuous on that disk, and then that the center is at AB, and that the gradient at AB is equal to 0. Now, let's go back and look at our 2 points. This definitely fulfills the requirement. If we plug this in, we're going to wind up with 0 out of our gradients. But this one is a little bit sketchy. In fact, the gradient doesn't exist here, remember? And anytime that the gradient doesn't exist at a point, we're not going to be able to apply the second derivative test. So we actually just simply ignore this point. And we're only going to apply the second derivative test to the point 1, 2. Okay. So our second derivative test requires us to compute all the different partial derivatives, or second partial derivatives. So let's go ahead and do that. Our second partial with respect to x is equal to 8 over x cubed, And our second partial derivative with respect to y is equal to 16 over y cubed. And our mixed partial derivative is equal to 8. So if we go back to what we need in order to do the second derivative test, we have to write out this expression right here. So d of xy is equal to, and now we're going to plug these pieces in, 8 over x cubed, 16 over y cubed, and then minus 8 squared. So this is just equal to 128 over x cubed, y cubed, minus 64. Before I go any further, I do want to point out and say that sometimes it's really common to plug your points in and then go through and compute the dxy part. You can do it in either order. It doesn't really matter. I personally find, and it actually doesn't really make a difference in this case or whatever, but in a lot of problems, you'll wind up with multiple critical points. And I find that it is the easiest to do this if you write out the generic expression like this and then plug in your multiple critical points. This time we only have one, so maybe it's not worth it to go to that much work. But just something to keep in mind, you can either plug your point into these pieces and then construct it here, or you can construct the generic formula and then plug your points in. It doesn't matter which. But anyway, the main idea here is, though, we still have to wind up with d evaluated at 1, 2. So we have 128 divided by 1 times 2 cubed minus 64. This guy is 8. 128 divided by 8 is, well, 16. So this is definitely less than 0, which means that now we are ready to go back and look at our second derivative test with cases. We're looking at case 2. D evaluated at 1, 2 is definitely less than 0, which means that we're looking at a saddle point. And that's pretty much all there is to doing that. So again, you just go through, you find your critical points, and then you figure out this expression here, the dxy is equal to this combination of your second partial derivatives, plug in the points, go through the cases, and then classify according to that. It's not too bad. Okay, so I want to introduce a theorem, though, because we've been talking about this idea of finding local maximums and minimums, but what about finding absolute or global maximums and minimums? Well, we have a theorem for that. So if we have that f is a continuous function, and this is defined on a closed and bounded set D in R, N. And if you don't know what closed and bounded mean, I recommend that you check out the video, open versus closed, bounded versus unbounded sets. It'll kind of clear that up for you. But anyway, so suppose that this function is defined on this set. Then if we know that that set's closed and bounded, we know that f attains both an absolute maximum and an absolute minimum. Okay, but one thing about having that it's defined on this closed and bounded set means that we have to have extra information, or what's called a constraint on the function f that we're working with. So just here's an example of what that would look like, and I'll work through this example here in a sec. We could have the function f of xy is equal to x squared plus 2y squared on a particular shape or something like that that's defined by another equation, say x squared plus y squared is equal to 1. This, because we have our equal sign here, is a closed and, well, it winds up being a bounded set if you were to graph it, because it's just a circle. So we have our closed and bounded set, and we know that f of x then has to attain both an absolute maximum and an absolute minimum. The problem is that if you kind of I mean, I guess you could probably approach this using a second derivative test, but it's really not necessarily the best way to do it, especially not as problems become more and more complicated. So we really need a new strategy for approaching this. And this strategy that you're going to use is called Lagrange multipliers. And what Lagrange multipliers says is that, first of all, this had to have come from maybe like a larger, I don't know, just like a different function. Say we can call this a general function of g of x, y. Okay, and what it says is that the gradient of f of x, y has to be equal to some scaled version of the gradient of g of x, y. Lambda is just some number that we're multiplying the gradient of g of x, y by. And we have to solve this equation and figure out where this holds true, and that will be our what we call constrained critical points. So possibilities for absolute maximums and absolute minimums following what's called this constraint right here. Just a quick aside, a little bit of terminology. If you ever wind up working in like a field of optimization, or I think there's a lot of different fields of engineering that use these. This is called the objective function. Or sometimes you'll call it the cost function. And this right here is called your constraint. Okay. So once we have our constrained critical points, all that remains, since we're looking for an absolute maximum and an absolute minimum, you just have to simply compare them to each other to see which one's largest and which one's smallest, and then you're good to go. But anyway, let's go ahead and walk through this process and see what this all looks like. I guess I'll start a new page for this. So fxy was equal to x squared plus 2y squared. And we're saying that we have the constraint x squared plus y squared equals 1. And we could also take this to be g of xy equals x squared plus y squared. Okay, so our gradient of f is equal to 2x for y. And our gradient of g is equal to 2x 2y. Oops, there should be an x there. So this gives us, we wind up with 3 sets of equations. We have that 2x has to be equal to 2x times lambda, because we said that gradient of f is equal to lambda times gradient of g. 4y is equal to 2y times lambda. And then we finally have this information right here from the constraint x squared plus y squared equals 1. And this will help us figure out what all of our constrained critical points are. Okay, well, at this point, you're just solving a system of equations. We have 3 unknowns, 3 equations. That's enough information to be able to solve this system. The first thing that you always want to check, though, is see, okay, what could be equal to 0, what may not be equal to 0. Well, there's not really any issue with x being equal to 0. So we want to consider x equal to 0 as a possible case. And then once we eliminate x equals 0 as a case, we're allowed to like divide by x and be able to solve a lot easier. So in this situation, there's no problem with x being equal to 0. So x could be 0. In this situation, x equals 0, and we look down here at our last equation, this means that we have to have y is equal to plus or minus 1. So then our constrained critical points from that would be 0 plus or minus 1. However, x may not be equal to 0, okay? So if x isn't equal to 0, this means that we would then have lambda equal to 1 as a result, because the 2x would be able to cancel from both sides since we're no longer worried about dividing by 0. So if lambda equals 1, we then have 4y is equal to 2y. Well, that makes no sense unless y equals 0. Well, if we have y equals 0, we must have x equals plus or minus 1. So now we have plus or minus 1, 0 as our other 2 critical points. So at this step, now we just have to check to see which one's going to give us the absolute maximum, which one's going to give us the absolute minimum. And we do that by checking f at all 4 critical points to see which is largest and smallest. Okay, so let's go ahead and do that. It's just some plug and chug, it'll be fine. So we have f at 1, 0 is going to be equal to, well, it's just going to be equal to 1. F at negative 1, 0 is negative 1 squared plus 0, so that's also just going to be equal to 1. F at 0, 1 is equal to, it'll be 0 plus 2 times 1 squared, that's just going to be 2. And then f at 0, negative 1 is also just going to be 2. Well, so this is our minimum, and this is our maximum. So plus or minus 1, 0, both give absolute minimums or minima, and then 0 plus or minus 1 both give absolute maximum. And it's very important that this is on the circle x squared plus y squared equals 1. The constraint plays a very, very important role in this. And we'll see why in just a second. So, but yeah, that's pretty much it to using Lagrange multipliers. Now, the really tricky part is just figuring out how to solve the system of equations. And I have a video that I'll post in a little bit about just working through some more complicated examples of that. Okay, now one thing that I do want to emphasize is that these two methods of optimization, the second derivative test and Lagrange multipliers test, sometimes have to work together to solve one problem. So. Okay, so an example of this would be when our constraint function doesn't just have an equal sign, but maybe has an inequality. So we're going to find the extreme values of f of xy equals x squared plus 2y squared. And this is just going to be on the disk x squared plus y squared is less than or equal to 1. Okay, so by the theorem that we had earlier, since we're working with a closed and bounded set, we know that f will achieve extreme values on it. So we're not too worried about whether or not they exist. It's just a matter of whether or not we're going to be able to going through and finding them. So there's a couple of steps that we want to do here. We're going to break this into a few parts. The first thing is that we're going to find regular critical points, not constrained critical points, just regular critical points on the inside of our disk, which is given by x squared plus y squared is less than 1. And we're going to do this using our typical method of letting the gradients be equal 0. So our gradient of f x y is equal to 2x and 4y, oops, which means that our only critical point can really be x, y, equals 0, 0. Okay, so this is either a local minima or a local maxima. I guess it could be neither. Which brings me to something I'll circle back around here in a bit, something that I forgot to say about the second derivative test. So we'll revisit that here in a second. The possibility that it could be neither. But anyway, but this only finds us like a local property. We need to have things to compare it to and know that we're on a closed set in order to know that we have an absolute or global minimum or maximum. But anyway, one thing that you do want to double check is the big thing is making sure that this does actually lie inside of this disk here. Well, 0 plus 0 is definitely less than 1, so we're good to go. Okay, so now what we want to do is find constrained critical points using Lagrange multipliers on the boundary that we left out, because we left out the part where x squared plus y squared is actually equal to 1. So in this setup right here, we now have the really typical setup for the Lagrange multipliers. So you just apply Lagrange multipliers for that. We actually already did that, and we have plus or minus 1, 0, and 0 plus or minus 1 as being our critical points from that. Okay, so these are all the critical points that we're going to be able to find on the disk. We checked the inside, we checked the boundary. Now we just have to plug them all into F and see which ones are the biggest and which ones are the smallest. So that's our step 3. Earlier we said that F at plus or minus 1, 0 was equal to 1. F at 0 plus or minus 1 was equal to 2. And F at 0, 0, well, that's going to just be 0. Okay, so this guy is our absolute max. And this is our absolute minimum. So remember how in our other example, we had found that this was our absolute max or absolute min? That was because we were only considering the edge of the circle. But now that the area that we're considering is larger, we were able to throw in some extra points, and we find that these are our new extrema. And again, this is really important that this is on the disk. X squared plus y squared is less than or equal to 1. Whatever your constraint is plays a really important role in determining minima or maxima. Okay, so that's pretty much all there is to that kind of process right there. But going through this reminded me of something that I wanted to make sure to mention about our second derivative test. And it's actually a feature that's, again, pretty similar to what you learned in Calc 1. We have a third case here, which maybe you mentioned this and you're like, oh, well, what about the case where that is actually equal to 0? Well, if it's equal to 0, it doesn't help us any. It's not conclusive, and you have to kind of try to look for some other methods to be able to classify your points. So if it's equal to 0, the test is inconclusive. And that's really pretty much all you can do with that. So yeah, sorry I didn't mention that earlier, but that is a third case to kind of keep in mind. But anyway, that's kind of the big idea behind the second derivative test and Lagrange multipliers. Again, second derivative test will give you local extrema, and then Lagrange multipliers will give you absolute maximum, absolute minimum, because you're working with a constrained set. So anytime that you're given a constraint, you want to use Lagrange multipliers in some form. So hopefully that's helpful. And in another video, I'm going to go over Lagrange multipliers in a little bit more detail with some more complicated examples. So I'll see you then.